Hello class, welcome to this video on probability statistics, chapter 3 test review. So we're going to review this packet in order to prepare you for the chapter 3 test. So it's broken down by the lessons, so we'll start with lesson 1. Identify the explanatory variable for the following relationships and explain your reasoning. So we want to also explain, not just write down whether it's explanatory or not, right? So we're gonna do the entire explanation. All right, so test scores and hours of sleep. So in this case, the hours of sleep is the explanatory variable because it helps explain the test score, right? So we're going to say the hours of sleep is the explanatory variable. Since it helps us predict the test score. All right, and then advertising, expenditure, and sales. So how much you spend on advertising could affect the sales. So advertising expenditure is going to be the explanatory variable, okay? So advertise expenditure is the explanatory variable. As it helps us explain changes in the sales. All right, the weight of individual and the weight of the backpack carried. So in this case, the weight of an individual can help us determine how much weight can be carried, right, in the backpack. So the weight of the individual is the explanatory variable. Helps us predict the weight that can be carried. All right, so the height of the individual and the shoe size. In this case, either one could help explain. The height could explain the shoe size. The shoe size could explain the height, right? Or can help us predict the height. So either variable is explanatory. Since either variable can help us predict the other. Weight loss and the amount of water consumed. The amount of water consumed can potentially help us predict the weight loss, right? So maybe if more water is consumed, then there's more weight loss. So the amount of water consumed is the explanatory variable, since it helps us predict the amount of weight loss. All right, so there you go. So that's explanatory. So number 2, researchers carried out a survey of 4th, 5th, and 6th grade students in Michigan. Students were asked if good grades, athletic ability, or being popular was most important to them. The two-way table summarizes the survey data. Okay, so we got to explain what the explanatory and response variables are. So in this case, the grade level of the individual helps us determine whether they think grades is most important to them, athletics, or popularity. So in this case, this is the explanatory variable because that helps us explain the response to the survey. Okay. So the explanatory variable is the grade level. And the response is their most important goals. So the most important goal. Okay. All right. So here we go. So make a segmented bar chart. So because this is the explanatory variable, this is going to go on the x-axis, right? So the grade level is going to go on the x-axis. We need to calculate the percentages of each of these. So for fourth grade, out of 92 fourth graders, 49 said that grades was most important to them, right? So in this case, we got 49 out of 92. We need to convert that to a percent. So 49 out of 92 times 100, that's 53%. Okay, so 53%. Let me just do it. Let me split this up. So this is 53%. Okay, and then this one's 24 out of 92. So let's do that one. So that's 26%. Okay, and the last one, 19 out of 92. That's 21%. All right, and then we got to do the same thing for fifth grade. So there's 50 out of 108. Out of 108 fifth graders, 50 chose grades. Okay, so 50 out of 108. Let's just do the other ones where we're at it. 36 out of 108. And then 22 out of 108. Okay, so we got 46% here, 33% here, and then about 20% here. It's not going to be perfect. It's not going to be a perfect 100 because we're rounding. Okay, so that's okay. It should add up to ideally close to 100. And then 69 out of 135 times 100. Then we got 38 out of 135. And then last one's 28 out of 135. So we got 51, 28, and 20%. Okay, 51, 28, and 20, and 21. So this is going to round to 1. Okay. All right, so that gives us our percentages, and then when we do our segmented bar chart, we're going to have percent on the y-axis. We're going to go by tens, perhaps 10, 20. All the way to 100. Okay, we got percent on the y-axis, we got grade level on the x-axis, 4th, 5th, and 6th grade. And then all these are going to go to 100. All right, and then, so they all stack up to 100, and then we need a key, right? So the key is for most important goal. Okay, so that's the key for the most important goal. So they chose grades. It was either grades, athletic, or popular. So for grades, let's just shade it. Athletic, let's just make it blank. And then popular, let's do that polka dot. Okay, so, all right, so we got 53% for grades, then 26 for athletics. So 53% for grades, so for 4th grade. So 53, that's around here, so this has got to be shaded. And then now the next one is 26%. So we got to stack it. So 53 plus 26, that's 79. So that's almost 80. Okay. That's almost 80%. Right around here. And that's going to be, this part is athletic. And then this has to be popular. All right. And then for 5th grade, it was 46% and then 33. So 46% is around here. Okay, and then we said 46 plus 33, that's 79. Again, that's close to, yeah, that's 79, close to 80. And here we go, we got the polka dot here. And then for 6th grade, we got 51%, then 28. Okay, so 51%. And then the other one, so that was 51, now it's 53. Okay, so this one's a little bit lower. And then we got 51 plus 28 is, again, 79. Okay, so there is a slight difference in the bars, not much, but it does exist. Okay, so so not much, but it does exist slightly, right? So 4th grade, there's a slight change compared to 5th and 6th between the athletic bars and the grades bar. The popular basically stayed the same, so that didn't change, but the other ones did change. Okay, so there is an association. As long as there's a few differences, then you would say yes, there's an association. Okay, so yes. There's an association between the two variables. The distribution of most important goal is not the same for each grade level. For example, 4th graders more likely to choose grades than the others. And 5th graders more likely to choose athletic ability. Okay, so there is an association there. There's a pattern there between the grade level and the important goal. All right, so let's look at lesson 3.2. At what age do babies learn to crawl? Does it take longer to learn in the winter when babies are often bundled in clothes that restrict movement? There might be an association between the baby's crawling age and the average temperature during the month when they first start to crawl, around 6 months after birth. So data were collected from parents who reported the birth month and the age at which their child was first able to creep or crawl at a distance of 4 feet within 1 minute. The table shows birth month, the average temperature, 6 months after birth, and then the average crawling age. So we want to make our scatter plot. So first you got to determine which one's the explanatory variable. So here the explanatory variable is the temperature, as the temperature may help us predict their average crawling age. Okay, so the temperature is something that we think affects their ability to be able to crawl. Okay. So therefore that's going to go on the x-axis, all right? And then this is going to go on the y-axis. All right, so the smallest temperature is around 30. The highest temperature is around 73. So let's go from like 30 to 75 and we'll go by fives, okay? So we'll do that. So we got the average temperature in degrees Fahrenheit. We'll start from 30, we'll go by fives. Okay, and then the smallest crawling age is about 28.58, and then the largest is in about 34-ish. Let's see, 33.64. So we'll go from like 28 to like 34, and we'll go by ones or something like that, okay? All right, and then this is the average crawl age, and the units are in weeks. Okay, and then we're gonna just graph it. So these are like coordinates, 66, 29.84. So the average temperature is 66 degrees, and then the average crawling age is almost 30. Okay, and we keep doing that. The next one's 73 degrees Fahrenheit, and then about 30.5. So 70, and then, or 73 rather, and then 30 and a half, like around there. Next one's 72, and then 29.7, like maybe around there perhaps. And then 63 degrees Fahrenheit and 31.8. 63, 31.8, close to 32. 52, and then 28.5. Like around there. 39 and 31.4. It's got to be closer to the 40. Okay, 33 and 33.6. All right, 30 and then 32.8. Uh, 33 and 33.83. Wait, 33.8. All right, and then 37, 33.35. Okay, 48, 33.38. And then 57, 32.32. All right, and there is our scatter plot, okay? That's it, so you're just graphing the dots, know which one is on the x-axis, y-axis, and then do your scale, all right? Okay, so describe the relationship shown in the scatter plot. So if I look at this looks like it's linear, right? It looks like it's kind of linear. That looks like and then it looks like it's pretty decent relationship. So I would say it's probably moderate strength, because most of the dots are pretty close to that line, right? If you were to look at that. So let's go ahead and describe it. Yeah, let's describe it here. It says it here in part B, but we'll just describe it here. So for part B, direction. Direction is negative. There's a negative association. It's going down. Form, it looks linear. Strength, it looks moderate strength. And then outliers. There appears to be an outlier right there. That outlier is for Looks like it's for May, 52 and 28.58. So yeah. So May at 52, 28.5. Oops, let me go back to it, sorry. May at 52 and 28.58 appears to be an outlier. Okay, so there is part B, and that's the description of the scatter plot. All right, so that's it for that one. Number 4, when flipping a coin onto a table, it is very unlikely to land on its edge. What if you glued several pennies together and then flipped the stack? The students in Mrs. Chauvet's statistics class collected data by repeatedly flipping stacks up to 27 pennies long. You can ignore this. The scatter plot shows the relationship between the number of pennies in the stack and the edge percentage. Describe the relationship. So we just want to describe it. So it looks, if you look at it, it looks to be curved, right? It looks like that. So it's non-linear. Okay, so first off, and it looks it's going up, so it's positive. So the direction is a positive association. The form looks nonlinear. The strength looks it looks pretty good, actually. A lot of the points are pretty close to that, so I would say it's pretty strong. Strong, since most of the points are pretty close to that curve, right? And then outliers, there don't appear to be outliers, so no apparent outliers. Okay, all right, that's it for number 4. All right, number 5, it appears to be a positive relationship. It appears to be, somewhat strong, so I could consider that moderate to strong. If you said moderate, if you said strong, that's fine either way. So I would say probably more on moderate. There doesn't appear to be any outliers, and it's going positive, it's going up, right? So the direction is positive association. The form, it appears to be linear. The strength appears to be moderate strength. And then the outliers, no apparent outliers. Okay, all right, so there's an example, and then he got one more example here. This one actually looks kind of curved if you look at that there, but it's kind of weak, right? Because the points are kind of scattered and far away from it. But so I would consider that maybe weak to moderate. But more on weak side because of these outliers, and then these points are very away from it. It's kind of loose, so I would say it's fairly weak, but it is non-linear. It appears to be. The direction, there's a negative. It's going down for sure. So it's negative association. The form appears to be non-linear. The strength appears to be weak. Or fairly weak, right? And then outliers, there appears to be an outlier there. And that outlier is around, it's United States, the 55,800 and then 56%. That's what that one is. The United States deviates from the overall pattern at $55,800 and 56%. All right, so that takes care of that one. This appears to be one outlier there. All right, so let's look at the next lesson. So look at problem number 3. Give an estimate for the correlation of this relationship based on the scatter plot. Okay. So we just, problem number 3. So that's this one right here, the baby one, the temperature, and then the average crawling age. So that we said that was moderate strength to strong, moderate to strong. So that's definitely, if it's moderate or strong, I'm going to put /strong. Then that means it's going to be probably closer to 0.7, 0.8, right? So, and it's negative. Okay, so it's definitely not that, because that's weak. It's definitely not this, because that's moderate, but it's too much on the moderate side. It looks stronger than just moderate, right? It's sort of like in between moderate and strong, or maybe you can consider it fairly strong. So this looks to be the best one. It's negative, and this one is too strong, so I wouldn't suggest doing that. And these are positive, so I can ignore those. Remember, the relationship is negative. So I would say negative 0.75 is the closest. The R is negative, right? And R is closer to -1 than 0 due to the strength. It looks pretty strong, so it's going to be closer to -1. So negative 0.75 is closer to -1 than it is to 0. All right. So number 8, classify the scatter plots as having positive, negative, or no correlation. So if I look at this scatter plot right here, it looks to be all over the place. It's scattered all over the place. So there appears to be no correlation. You see, half of them are above, half of them are below. No correlation for that one. Doesn't appear to be going up. It doesn't appear to be going down. It appears to be flat. Now this one, on the other hand, appears to be going down. So that's negative. This appears to be going up, so that's positive. This appears to be going up, so that's positive. This appears to be going down, negative. And this, again, doesn't look like it's doing anything. Half of them are above, half of them are below. It's all over the place. I mean, it's not even, there's no relationship there. So it's no correlation. Okay. All right, that's it for number 8. Number 9, which of the scatter plots shown above suggests a strong negative correlation? This is positive, right? And it's strong, it's fairly, it's decent and positive. This is curved and positive, right? This is like curved relationship, so definitely not that, and it's positive. It's going to look upward. This is no correlation, so it can't be that one. This one is fairly strong and negative. So it's got to be grafty. All right, so okay, so this is probably the part that a lot of students are going to struggle with, is the calculation. So you're going to be given the formulas on the formula sheet. So the formula for R, which I can write over here, is the sum of zx, zy divided by n minus 1. That's how you calculate R. Now the formula for zx is, which I can write over here. Let me write it over here. Is x minus x bar divided by sx. Okay. The formula for zy is y minus y bar divided by sy. And of course, I don't want to write on top of that. So let me just write this over here. So the formula for that is x minus x bar divided by sx. The formula for this guy, y minus y bar divided by sy. Okay, and so what we got to do first off is on the calculator, we need to calculate x bar, y bar, sx, and sy. All right, so you need to know how to do that on your calculator. Now I'm going to be doing this on Excel. Okay, because Excel is going to help me get those those values. So you can follow along if you want. So I'm going to show you that on Excel. Okay, so I'm on Excel. I'm going to go ahead and do my x, let me make some room here. So I'm going to do my x bar. I'm going to do my y bar, sx, sy. All right, and then we're going to calculate those, and then let's do x, y, zx, zy, zx, zy. Okay, we're going to type in our x values. So from our data, which I'm just going to type them in because I can see it from the paper. So just type in the data that they give you on your calculator, in this case Excel, if you want to follow along with calculating that. And then here are your y values. I'm just type them up real quick. Again, typing these in on the calculator can be a pain, but you just got to be careful when you're typing them in. If that's the hardest part, is typing in on the calculator, then that's not so bad. If the calculator is doing the work for you. All right, so we got x and y. Now we're going to calculate the x bar. So this is what you would do on a calculator. So equals, we're going to do the average. X bar is just the average of the x's. So we're going to do the average of those values. It gives us the average there. Equals, we're going to do the average of the y values. Oops, I gotta just select these. There you go. And then I'm going to do the SX. Now, they said in the problem that they want us to round to 2 decimals, okay? Except for the correlation coefficient, they want us to round to 3. So let's round this to 2 decimals, 31.77, okay? All right, and that's 50.25, so we can leave it like that. Now, SX equals standard deviation, STDEV, dot S. That's the standard deviation for the sample, S. And we want to do this for X. Okay, and then equals standard deviation to dot S for Y. Okay, and round this to 2 decimals, so that's going to be 15.85. And then this is going to be 1.76. I'm just going to do that. I'm just going to type it in. Okay. All right, so now we are going to, so now to get this row, you have to take, so to calculate ZX, remember, you have to do X, which is 66, minus X bar, which is 50.25, divided by SX, which is 15.85, okay? So equals, parentheses, X minus X bar, and I'm gonna use the dollar key for that because I don't want this to change, divided by SX. Oops, I picked the wrong one. This one, SX. And if you're following along on Excel, I'm using the dollar key because I want to keep this constant. I want to keep it fixed. I don't want to change the value. All right, there you go. So 0.99, and then I'm going to copy and paste this formula here. Again, to get this one, you do the X minus X bar divided by SX, right? That's how you would get this ZX here. If you want to get this ZX, you got to do 72 minus 50.25 divided by SX. And that's how you get each of these. All right, now let's do the ZY equals, ZY is Y. You got to make sure you put parentheses when you do this on the calculator. Y minus Y bar, I'm going to use the dollar key, divided by SY. If you want to do the dollar key, what I'm doing, it's F4. You got to hit F4 on the keyboard. All right, enter, and then copy and paste that formula. So this does it for all of them. Okay, and then now you got to multiply these two together. So for the last column, equals this times this. Multiply them. All right, and then you just copy and paste that so that we don't have to do it a gajillion times. The computer can do it for us. And then you take this column and we add it. So we want to do the total. So we want to do add this together, and you get this. All right. Then you take that number to get your R. You take that number and you divide by n minus 1. Well, how many numbers do I have? I have 12 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my n is equal to 12. Okay? So I'm going to divide by 12 minus 1. Or 12 minus 1 is just 11, right? So I'm just going to divide by 11. Okay? And that's my R. Well, let me go back so I could show you the to this part. Okay, so again, if I want to get this value, you take 66 x minus, let's write down the values that I got on here. Hold on a second. Yeah, I forgot to write down the values for some reason. Yes, okay, so I'm gonna need to write down those values. Okay, so let's go back here. Okay, so we got X bar, 50.25, 31.77. So I'll go ahead and write down those values real quick. Okay, so I'll go ahead and went ahead and wrote down those values from the Excel, from the calculator. All right, so we got, to get ZX, we got to do X minus X bar, right? So 66 minus 50.25 divided by SX, which is 15.85. Okay, we'll do that on the calculator. We get about 0.99. We want to round to 2 decimals, all right? So 0.99. So if I do that, if I do this 73 minus 50.25 divided by SX, okay? So if I do that, for the second row, I get 1.44. For this one, I would have to do 52 minus 50.25 divided by 15.85, right? So I'm just going to write down those numbers. So 0.11, this would be negative 1.09. This one is negative 0.84, and then this one's 0.43. All right, let me do ZY. So ZY is going to be Y minus Y bar divided by SY. Okay, so 29.84 minus Y bar divided by SY, 1.76. So if I do that, round to 2 decimals, I get about negative 1.10. All right, and then this is negative 0.71. If I do that, negative 1.81, 1.06, 0.90, and then 0.31. Again, using the same process. And then to get the last column, you multiply those two numbers, 0.99 and then negative 1.10. So let me show my work. This times that. I get negative 1.09. And I got to do the same thing for the rest. Negative 1.02, negative 0.20, negative 1.16, negative 0.76, and then 0.13. All right, so after you do that hard work, you get to take this column and you got to add it. So that's what this is for. Remember, this means you add, right? The little sigma symbol. So you got to add that last column. So if I add those numbers together, I get a negative 7.74. And that's the total. And now we can get R. So we're going to take that total and we're going to substitute it in. Substitute it in for the numerator. Okay, so we get negative 7.74 divided by n. N is 12. We got 12 numbers minus 1. So 12 minus 1 is 11. So this divided by 11 is approximately negative 0.700. That is my correlation R. Okay, and that's how we do on that problem. All right, now we want to interpret it. So let's interpret the correlation. Correlation means linear relationship. Okay, so to interpret, we have to say the linear relationship, keyword linear, between the average temperature 6 months after birth and the average crawling age is, so negative 0.7 is pretty decently strong. We could say moderate, that's fine. Is moderate, or if you said, you know, borderline moderate strong, moderate and negative. Okay, and that's how you interpret that correlation. So the linear relationship between the two variables is moderate and negative. What effect does the point for May babies have on the correlation? Okay, so let's look at the outlier. So for the May outlier, So if I go back to the graph, which is not this one over here, number 3. So this one that I circled, what does that have to do? What does that do to the graph? Well, because that outlier is far away from the data, the pattern, it's going to weaken the correlation, right? It's going to weaken the relationship. So that's all we got to say. It's going to weaken the relationship. Okay. So what effect does the may have? The point, the outlier is far away from the linear trend, so it will weaken the correlation, making it closer to r equals 0. Okay, so it's going to make it weaker. It's going to move it closer to the 0 side than there's anything. It's not good. That doesn't mean that it's going to be close to 0. That's just saying it's going to make it closer, weaken it. How would the correlation be affected if the average crawling age were reported in months instead of weeks? Now, this is important. The units of correlation, there's no units for correlation. Okay, so that means it doesn't matter the units that you use. If it's months, weeks, years, whatever, it doesn't matter. If you change the units, it's not going to change the correlation. So that's the good thing about it. Is the correlation would still be, the correlation would remain negative 0.700 since correlation is not affected by units. Or by changes to units. All right, and that's it. All right, so next one. The principal of a high school read a study that reported a correlation of 0.79 between the number of calculators owned by high school students and their math achievement. Based on this study, he decides to buy each student at his school 2 calculators, hoping to improve their math achievement. Can the principal conclude a causal relationship between the number of calculators and the math achievement? Explain. So in other words, can we conclude cause and effect? The answer for this question is always going to be no, guys. When you see a question like this, okay, they give you the correlation. There's a correlation between the 2, yes. But does that mean that one caused the other one? The answer is no, right? It doesn't matter if this R is 0.9999, okay? It doesn't matter if it's a really strong correlation or anything like that. It's still not going to be, it's still not going to conclude cause and effect, all right? Because there could be other variables at play. We don't know if there's another variable that also would lead to that same, relationship. Okay, so although there is a strong correlation an increase in number of calculators is unlikely to cause increase in math achievement. These variables might be affected by other variables like family income or how much the student values education, etc. Okay, so it's probably okay if we have family income and then the students value education. Well, then they're going to have calculators, right? Because they're going to be buying the calculators because they have the income for it, and they're gonna buy all the materials that they need, right? So that might be a factor. There's other factors involved, right? It's not just The calculators may have caused the math achievement. There are other factors. So I'm going to put here no. And then although there's a strong correlation, it's not likely to cause an increase. All right, so the answer to this question is always going to be no when you see questions like this. And then it's just a matter of explaining a little bit, okay? All right, so lesson 3.5. The Nenana Ice Classic is a contest held each spring in Nenana, Alaska. For the price of $250 per ticket, contestants guess a date and time when the ice will break on the Tanana River. On 2019, the winning guess was worth more than $300,000 if they were to guess the date and time when the ice will break up. The scatter plot shows a relationship between y equals ice break day, number of days into the year when the ice breaks, and x equals the number of years since 1900, with the least squares regression line given here. Predict the date when the ice will break on the Tanana River in the year 2050. How confident are you in this prediction? Now remember, these are the years since 1900. So for example, 20 years would be 1920. This is 1940. This is 1960, 1980. This is the year 2000, right? 120, that's the year 2020, okay? So if you want it to be at 2050, then that's got to be 150 years out, okay? So what we're going to do is the x is going to be the year 2050 minus 1900. So that's 150 years, okay? That's the number of years since 1900. All right, so you're going to plug that into here, okay? So y hat equals 130.49 minus 0.0861 times 150. You just plug that into there and get your answer. So we get 117.575 days. All right, and then this, and we're not going to be confident in this. We shouldn't be comfortable. So not a good guess or not a good prediction. Because the reason why it's not a good prediction is because we don't have any, it's a prediction outside of what we collected. 150 years is over here, and we don't have any data on that. So it's going to be a poor prediction, okay? That's called an extrapolation. So not a good prediction because there's no, because the prediction is outside of the data collected. Okay. Part B, calculate and interpret the residual for 2019 when the ice broke on day 104.01, just after midnight on April 14th. Okay. So again, we need to remember the residual is y minus y hat, right? And so this is y. The y hat we have to calculate. It says 2019, so x is equal to 2019 minus 1900. So that's actually 119 that we got to plug in for x, okay? So we're going to plug that into the y hat equation. 130.49 minus 0.0861 times 119. Plug it into the y hat equation. And when we plug it into there, we get 120.24 days. Now we can plug that into y hat. So we get 104.01 minus 120.24 is negative, you're going to get negative 16.23 days. All right, so the residual is negative. That means that we over predicted what it was going to be. Okay, so that means that the actual ice broke 16.23 days before the date that we predicted, right? Or earlier. Okay, so that's what that means. So interpret, so the interpretation. In 2019, the ice broke 16.23 days earlier than predicted by the regression line. Okay, if it was positive 16.23, that means we underestimated and it would be later than was predicted, right? So that's just, an example. All right, so interpret the slope of the least squares regression line. Okay, so this is the slope. The slope is negative 0.0861, right? Okay, so the slope is negative 0.0861 over an invisible one, right? Now, remember, slope is units of y over units of x, okay? So what are the units of y in this example? The units of the 0.0861, the units of y are the number of days, right? And the units for x is the number of years since 1900. So this is 1 year since 1900. Okay. So that means that for every year since 1900, that means the ice break, the day that the ice will break decreases by that many days. Okay, so the predicted day that the ice breaks, or the ice will break, I guess we can say the ice will break, decreases, because it's negative, right, by 0.0861 days for each 1 year increase since 1900. Okay, so that's how you interpret the slope. The y-intercept is 130.49. That's the y-intercept, okay? So 130.49. Does the y-intercept have meaning in this case? The y-intercept is when x equals 0. So when x equals 0, that means that the year is 1900, right? So yes, it does have meaning. Yes. What it means is that the predicted day, the predicted day for the ice break is, and what was the number? The number was 130.49. Is 130.49 days into the year. In 1900. That's when x equals 0 is the year 1900. Okay, so in the year 1900, when x is 0, the predicted day for the ice break is 130.49 days. All right, so there's that one. So let's look at number 12. One of the major attractions in Yellowstone National Park is the Old Faithful geyser. This scatter plot shows the relationship between x equals duration of the previous eruption and y equals the wait time until the next eruption. The equation of the regression line is given. Okay, predict the wait time if the previous eruption lasted 4 minutes. The previous eruption lasted 4 minutes. That means x is equal to 4, right? So x equals 4. So we got to plug it in. So y hat equals 33.35 plus 13.29 times 4. We just got to plug it into there. And we get 86.51 minutes. So that means we would have to wait 86.5 minutes. If the eruption lasted 4 minutes, we would have to wait for the 86 minutes for the next eruption. Predicted. In one cycle, it actually took 62 minutes between eruptions. So this is my actual y. And the duration of the previous eruption was 2 minutes, so that's x equals 2, okay? Calculate the residual for this cycle. All right, so then the y hat equals 33.35 plus 13.29 times, we're going to plug it in for 2 minutes. So that gives us 59.93 minutes. But the actual y was 62 minutes. Okay, so the residual is y minus y hat. So 62 minus 59.93 is negative 2.07 minutes. And they want us to interpret that. So that means we over-predicted. That means that the actual, I guess you could say, the actual wait time between the eruptions was 2.07 minutes. Did I get positive or negative here? I'm sorry, I put negative here. That's not a negative, that's a positive number. Sorry. It's positive 2.07, which means we under predicted. So that means that the actual wait time was 2.07 minutes above or longer than what we predicted. So the wait time between eruptions, I'm sorry about the writing there, was 2.07 minutes longer than what was predicted. By the regression line. Okay. Interpret the slope. So let's go back to the slope. So the slope was 13.29. That's the slope there. So 13.29. What are the units over an invisible one? What are the units of y? The units of y are wait time in minutes. The units of x are the duration, right? So 13.29 minutes wait for every 1 minute duration of eruption. Sorry, not explosion, eruption. Okay, so units of y over the units of x. So, and this is a positive. So that means for every 1 minute increase in the duration of the eruption, we have to wait even longer. It adds a predicted amount of 13.29 minutes to our wait time. Okay, that's what it's saying. So the longer the eruption, the longer we need to wait before the next eruption. And it's about 13.29 minutes for every 1 minute added. Okay, so that is our slope. So the predicted wait time increases by 13.29 minutes for every increase of 1 minute in the duration of the eruption, of the previous eruption. Okay, all right, so then we got E. It says, does the y-intercept have meaning in this case? If so, interpret the y-intercept. If not, explain why not. So, all right, do we have a meaning for x equals 0? Can we have a duration of a previous eruption of x equals 0? Okay, that doesn't make any sense. If you have x equals 0 for the duration of a previous eruption, that means that how can you have 0 minutes for the duration of an eruption? That means an eruption never happened. But then that contradicts, because there has to be an eruption, right? So if there has to be an eruption, then there can't be x equals 0. So it doesn't make any sense to have an eruption of duration 0 minutes. So here the y-intercept does not make sense. Okay, so no, because it doesn't make sense to have an eruption of duration 0 minutes. Okay. All right, so there's an example of where the y-intercept does not make sense. All right, so let's go ahead and wrap this up here. So we got 13.6. We got a couple of questions for that, and a couple of questions for these, and then we'll wrap it up. All right, so lesson 3.6. Here are prices and screen sizes in inches for 7 different sizes of one brand of LED HD television. Calculate the equation of the least squares regression line. Round each value to 2 decimal places. Okay, so again, we're going to need to do this on the calculator, plug these numbers in. But again, I'm just going to give you the values since I showed you how to already do it on the Excel. And I showed you how to do it in the calculator in class, right? So I'm just going to give you the values here. So if this is X. Yeah, this is X. This is Y. Okay, so if you average all the X's, you get 46.43. You average all the Y's, you get 604.29. You do the standard deviation for X, 9.61, standard deviation for Y, 247.92. Again, these are all on the calculator. And you can calculate R on the calculator. I'm going to show you how to do this on Excel, actually, because I haven't shown you how to do that yet. So let me show you that. Okay, so let me show you again how to calculate R. It's really easy to calculate R. I showed you how to do it on the calculator, but I didn't show you how to do it on Excel. So let me do that real quick. These are the screen sizes, and then these are the prices from the original example. All right, and then so now to do the correlation, you can type in equals correl. That stands for correlation, parentheses, and then you select this number, comma, and then these numbers. And then there's your correlation, so it's 0.984. Okay? So we can go ahead and go back here and say, okay, so R is 0.984. Okay. Now, to calculate the equation of the least squares regression line, you have to use the formulas, which are going to be given on your formula sheet for B and A. So here's your formula for B is R SY over SX. So once you calculate these, you can just plug it into that formula. So we get R is 0.984 times SY is 247.92 divided by 9.61. So you multiply those two numbers here and then divide by 9.61. So you get 25.39. Now to calculate A, the formula for that is Y bar minus B X bar. Again, you don't have to memorize the formula. These will be given to you. So now you can plug those in. You're going to plug this into B, and you're going to plug in your Y bar and X bar into that formula. So Y bar is 604.29 minus the B that we just found, the 25.39. The X bar is 46.43. And then we get, let's do that on the calculator, and we get negative 574.57. Now remember the equation of Y hat. Let me write the equation for Y hat over here is A plus BX, okay? And so you're going to plug in your A and you're going to plug in your B into there. So the Y hat equation is negative 574.57 plus BX. All right, and there it is. There's your equation. That's how you do it. It's really easy. It's not that hard. The hardest part is just doing the calculator and getting those numbers. Okay. So let's show you how to do this for this example as well. Okay. Now remember I showed you how to calculate X bar S. So I'm just gonna, assuming that you plug these into the calculator, these are your X values, by the way. So you're gonna plug all these into the calculator, 1, 2, 5, 6, 7 for your calculator, and then your Y values are your weights. Okay. You can type all that into the calculator and get your X bar. All right. So if you average the X values, you get 11.13. Again, highly suggest doing this on Excel or some kind of software to help you calculate X bar, Y bar. unless you have a scientific calculator. Yeah, y bar is 62.93, sx is 6.52, sy is 41.24, and r is negative 0.998. Again, all those on the calculator. And then now, once you get those on the calculator, use your formulas from your formula sheet for this. So plug in your r, plug in your sy, then plug in your sx. Okay, do that in the calculator, you get negative 6.31. Your A formula, y bar minus bx bar. So you got your y bar, 62.93 minus negative 6.31 times 11.13. And you get your A is 133.16. Okay, so then your equation of your regression line, y hat equals A plus bx. Now since b is negative, I could just put minus. All right, and there's your y hat equation. All right, and then the last thing here, we're gonna wrap this up almost, so is being able to, given a regression line, looking at outliers to see how it affects the equation of the regression line. How does it affect the y-intercept? How does it affect the slope? Those are kind of the things you want to identify, okay? Now the rules are as follows. So if looking at this data, my average x value is around here. Most of my data is here, which means my average x values is around here, right? X bar. And so now if the outlier is close to your x bar, then that means it has polling action. It's going to pull the line up or pull it down, depending on if it's above or below. If the outlier is far away from the x bar line, it's going to have swinging action. And so it's going to swing the line. It's going to swing it that way, closer to it. But if it swings that up, then it's got to swing this down. So it's got to be a swinging action. Okay, so let's do student A first. It's gonna, since it's far away from x bar, it's gonna swing this left side up, which means that the right side is going down. If the left side goes up, that means that the y-intercept increases, right? The line is gonna be more like, it's gonna be more like this, right? It's very bad. I'm trying to draw it the best I can. Okay, there you go. So it's kind of like that, where it goes down on the right side and it goes up on the left side. I'm trying to draw that more up. There you go. That's a little better. So that means that the student A is going to increase the y-intercept. And it's going to make the line flatter, right? So it's going to decrease the slope. So decreases slope. In other words, less steep. Okay. Now, so that's for student A. Really easy. Now, student B is now going to have, if I look at student B, it's close to your x bar line. So that means it's going to have a pulling action. It's going to pull the line up. So it's going to take this red line, it's going to pull it up. Okay, and that's all. It's literally just going to pull it up. So if it pulls it up, that means that the y-intercept increased. That also means that the slope stays the same. It's kind of parallel, right? So the slope, the y-intercept increases as well, but the slope remains the same. Remains roughly the same. So minimal change in the slope, okay? And that's how you do that. Okay, we could do this example here. So here's an outlier. What does it do to the equation? Well, this is where most of the data is. The average of that data is around here if you were to average the x bars, right? Roughly, it's just a rough estimation. It's not an exact number. So there's your rough x bar. This is pretty far away from that, so it's going to have swinging action. It's going to swing this closer to that, and then by doing that, this swings that way. So then the equation of the line is going to look like that, right? And so what that does, it increases the y-intercept. And then it makes the slope steeper, right? So it increases the slope, which means more steep, more negative. So that's what we mean by that. It increases the slope, it makes it more negative, it makes it more steep. Okay, and that's it. So that's what it's going to do. All right, that's going to do it for the video, guys. Hope you found this useful and informative. And as usual, I'll see you in the next one.